I will begin with a word of prayer. Heavenly Father, we thank you for this day. I thank you for these students. Just ask you to bless our work today, Lord. In your name I pray. Amen. All right, I will behave. So I wanted to talk, now I usually refer to these as deformation theorems. In, Calculus 3 typically, or sometimes complex analysis is another place where this comes up. But two-dimensionally, here's one. If you had the situation, it's kind of like a bunny, sort of. Anyway, suppose it's counterclockwise oriented, so like so, right? And you could take this curve, right, whatever it is, and you can talk about the integral of a vector field along the curve, right? This would describe the work done by the force field as you travel along the curve, or you could also refer to it as the circulation. It describes how the vector field's lining up with the path, and it gives you a measure of that. If the vector field in question, which I've not pictured, was everywhere perpendicular to the path, it'd give you 0. Right? So it's like it has to line up. Now, so just for the sake of specificity, let me call that P dx plus Q dy. Right? So here, I'll let F be the vector field PQ. So one of the things you can prove is if you had another curve, all right, like say here, like that, right? And that curve was also counterclockwise oriented, like that, right? And then suppose, in addition, that between those two curves, there was, like in this region up in here, you had the vector field satisfy the closed condition. So the closed condition, I mean by that, is partial q, partial x, equals to partial p, partial y in the green area. Right? If it satisfied this condition, then what you can do is you can argue that this is in fact equal to the integral over, I need to give the inner loop a name, let's say C. Let's call the second one C2, we'll call the first one C1, okay? You can prove that the integral over C2 of P dx plus Q dy is equal. Now this would be a deformation. This would not be a homotopy with fixed endpoints, right? I mean, this would be something else entirely. We haven't even talked about what this would be. But you can see it's kind of related to the notion that we talked about last class, right? I mean, we took a pair of curves and fixed endpoints, right? So to make it tie into last class, I would need to maybe pinch them. If I did this, then I could talk about I could talk about the endpoints being this point, both for the C1 and C2. These would be loops. Like the C1 would be deformed into loop C2. All right? So the way this is proved, right? But if you don't mind, I'm going to go back to the not pinched one, okay? Although admittedly, I can't directly connect with my notion of homotopy then. Fine. I'm at peace with that. So the way to prove this is you cut it into two pieces, all right? Actually, let me refer you to Green's theorem with a hole. So Green's theorem with a hole says that the integral over some bounded region of P dx plus Q dy is equal to the double integral over the region of partial q partial x minus partial p partial y dA. So this is Green's theorem. It's true whether it's true for regions which are not simply connected but are still bounded. the thing is, if you do this, then you have to come to the agreement that the boundary of the region is positively oriented. So like here, the region I'm talking about is this green thatched region. I mean, this is R. So like the boundary of R here by construction is C1 and then minus C2. Minus C2 because the inner loop is not oriented in the positive sense. If you can imagine yourself as a little dude walking along C2, la 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 la, the green thatched region is on your right. But the rule for orientations is if you imagine yourself walking along the edge of positively oriented boundary, the region should be on your left. So that would be minus C2. So the boundary of R is C1 minus C2. So this is C1 minus C2. And if you do an integral over a sum, well, of curves like this, this gives us the integral over C1 of f dot dr minus the integral over C2 of f dot dr equal to, what's this? Well, by the closed condition, that's straight up 0. Right? So we're able to, so that implies my claimed result, which is that the integral is the same over curve 1 or curve 2 because we can deform curve 1 into curve 2. Although I won't attempt to give a careful definition for that. I won't try to formalize that deformation, okay? I mean, I think we just drop what? I think we drop the third and fourth conditions of fixing the endpoints. So I'm not sure exactly what that involves. I'm not sure if I've ever looked at that carefully. I mean, not recently anyway, but that's an example of a deformation theorem. So these two curves are like homotopic, I think. I'm abusing the terminology slightly there, right? But you can get from one to the other without snagging. For us, whether or not you're snagging, I would be looking for points where the closed condition's not met. Right? Like a place where this is not met is a place I couldn't scooch past. I mean, I couldn't apply Green's theorem if there was a place where this was non-zero, then I wouldn't be able to like trade my integral over C1 from an integral over C2 or vice versa. So I had to watch out for spots where the closed condition's not met in terms of like calculus. A rather famous example of this would be the integral. If you integrate d theta around the unit circle. Counterclockwise oriented. What's d theta? The derivative of the inverse tangent, right? That's mostly true, not quite true. It's a slight abuse, but this is just a motivational comment, right? So let me call that unit circle C. Anyway, what do you got? You got yourself a I'm not disagreeing, but I'm trying to take the differential in my head. I want to write it with x squared plus y squared downstairs, and I want to write upstairs minus x dx. I think it's minus y dx plus x dy. Because I differentiate with respect to x, that gives me a minus 1 over x squared, which then I multiply through to get the x squared plus y squared downstairs. And the other one I differentiate with respect to y, it gives me a dy, which I again have to multiply by x to get the x squared downstairs. So that's why there's an x dy and there's a y dx. There's a minus because the derivative of x is minus x. 1 over x squared, minus 1 over x squared, derivative of 1 over x, blah, blah, chain rule. But the larger point here, Emily, is just that this you can just straight up calculate. What's the integral of theta over the unit circle? What's the change in standard angle over a unit circle? How many, if you go all the way around a circle, what's the change in standard angle? No. Pi? 2? I'm going to take those things together. I'm going to take those things together and put a 2 pi here. But yes. So the net change in theta around the circle is 2 pi. Right? But this, so we have an integral around a closed loop, which is equal to 2 pi. What does that say about this vector field? What does that say about the vector field f of xy equal to, minus y over x squared plus y squared, x over x squared plus y squared? It says that this vector field is not equal to the gradient of the theta function, actually. I mean, it's not, that's not maybe the wrong thing to say. Let me say it's not equal to the gradient of, let me use a different letter. It's not equal to the gradient of phi. It's not equal to, it's not a conservative vector field, because if it was, what's the integral around a loop? 0. So, I mean, this, in fact, is a lie, right? I mean, this is not, you're like, wait a minute, isn't that that's what phi is. Phi is the inverse tangent of y over x. If I differentiate that, that's the potential. But the thing is, this comes with strings attached, namely, x is non-zero. So you can't define an angle function that goes all the way around. There has to be a jump discontinuity, and that's why this is a non-conservative vector field. So what I'm trying to get at here is that if you look at, basically anything, here's the origin, all right? If you take any loop around the origin, like so, right? And if that loop is either inside or outside of the unit circle, and it's also counterclockwise oriented, then the integral around such a loop, let's say C2, and unit circle, you can actually check, it's not obvious, but if you partial differentiate this with respect to x, it's equal to the partial derivative of that with respect to y. In other words, this vector field satisfies the closed condition, which means that I can deform any integral of this vector field from a path which encircles the origin to another path that encircles the origin the same number of times, and I won't change the integral. The integral around the lumpy path is still 2 pi, because the integral around the unit circle works out to 2 pi. This is the deformation theorem. I do need, like, a self-intersection is going to get us into trouble. Going around this, going and circling it more than once is going to get us into trouble. Well, it can intersect it. It's self-intersecting once, but not, like, it can't keep covering the same paths more than, yeah. So the issue here is really topological, is the deeper thing, though. It's because the space, the domain for this vector field is actually the punctured plane, not the whole plane, right? Because this division by 0 throws out the origin. That's at the heart of this, like, non-trivial. That's why there's part of why it's possible to have a non-trivial integral. So I think these things actually start to be verified using homotopy as we go on in this section in Game 1. Like, eventually some of these things will be proved in a kind of different way and from a different angle in Game 1. But this is one of the reasons we're interested in homotopy, is because it's related to this issue of, like, deforming one integral into another. In fact, a lot of the origins for topology, if you go back and study why people were looking at questions of topology in the late 19th century, it was in no small way related to the problem of them trying to find like potential energy functions for forces in mechanics. Because when you think hard about those questions, they force you to think about domains. You can do a lot of physics without thinking about domains, right? But once you start thinking about potential energy functions, right, you'll find, even for relatively unsophisticated examples, that maybe you can't define a potential energy function all the way around the circle. Like you have to do it only locally. That speaks to an underlying topology, actually. I think I've said enough. I don't know if that helps or not. There's also a corresponding deformation theorem for surface integrals. Like you can, if you can go from this surface to like that surface, right, and the curl of the vector field is equal to 0 in between the two. So if this is like S1 and this is S2, and suppose like the curl of F is 0 out here, I mean, there could be a hole in here, and something interesting could happen inside the hole, let's say. You can prove that the integral around the boundary of the first surface is equal to the integral around the boundary of the second surface if you have the curl of the vector field 0 between the surfaces by Stokes' theorem. But anyway, let me get us back to game 1. Let me just say that we'd like to more precisely understand my claim that these examples were topological, because I think that's a very fuzzy claim right now, given what we've done. Right? Like I said, I claimed it was somehow topological. What do I even mean by that? Right? I think that's a fair question that we have not answered yet. All right? So, homotopy. Let's start at the fundamental group, section 3. So he says a pointed space and he uses XB as a pair. Right? Right. And here, B is, a point in X, all right? And he says the point B is referred to as the base point of X. All right, and he says he says a loop in X based at B is a path that begins and ends at B. So if this is B, right, a loop is like that, right? So gamma of 0 equals to gamma of 1 equals to B, gamma, a mapping, of course, from 0 to 1 into the topological space X, right? Just like we talked about last time, it's a path, but the new wrinkle is it begins and ends at the same point. It's called a loop. Path with the same initial and terminal point. And now he says that the product of any two loops based at B is well defined, so that the product of homotopy classes of any such two loops is well defined. And he says we're going to denote pi 1 xb to be equal to what? The set of homotopy classes of loops through, well, let's say loops at B. Let's say that this is a loop at B. just to have a language for it. I'm tired of saying so much.
What does it mean by when you say it's well defined?
Well defined. Well, it's a set of homotopy classes, right? So this is technically speaking gamma. Gamma. Well, it's this, such that gamma is loop at B. So like if we took two loops, so this one's gamma, right? So take another loop, beta, let's say. Then if I was to take the product of gamma and beta, that he's saying that this is unambiguously defined as gamma beta. Well, notation we've justified last time. So like, if we take the join of gamma beta, right, which is to say that we take gamma, run at double speed, followed by beta, run at double speed, that gives us a new path, gamma beta. And the so I mean the proof, of course, is that if we had gamma 0 equal to gamma, if we had bracket gamma, we had this last time, right? Gamma 0 equal to gamma 1, beta 0 equal to beta 1. Both these two things together implied what? So that was the fact that we could multiply homotopy classes by simply multiplying representatives in the sense of joining them by our double speed construction. I mean, there's a little bit more here to think about. Before we had to fix endpoints, now we have to take loops to loops, right? But if you think about it, if we compose a loop with a loop, we still got a loop. If that doesn't seem too loopy to you. So we go here, and then back. So we started and ended at B, right? Half the time, another half the time, full time 0 to 1. So the run two loops one after the other, you still got a loop. But otherwise, our construction of the set of homotopy classes with fixed endpoints, all of that stuff we did last time still goes through. It's just now the fixed endpoints are fixed to be the same point, which is the place we're basing our loops at, right? Okay, so then what? So this is the so-called, what does he say? Fundamental, oh, I haven't said it yet, but some name calling that I should do. This is the fundamental group, right? Fundamental group of, oh, come on, of X based at B. All right, theorem. He says let B and C be points in X, all right? And suppose alpha is path in X from B to C, all right? Then for each loop, gamma based at C, the homotopy class alpha sub star parentheses bracket gamma close parentheses is equal to alpha gamma alpha inverse. is defined and alpha star is an isomorphism of the fundamental group of X based at C and the fundamental group of X based at B. Something he doesn't do, but I think everybody should do when you're talking about this, is to draw a picture to explain what's going on, right? Let's try to draw a picture to say what's going on. So the picture here is something like this. Here's the universe in which things are happening, X, right? I'm starting here at a point B, right? I'm going over here to some other point C, okay. Alpha gets me from there to there, okay. And what's the object of consideration here? A loop gamma based at C. So what's that look like? So like here's the loop, right? So that's the loop gamma based at C. The claim is that that gives us a homotopy class alpha star. Now what he doesn't tell us is where is alpha star of gamma? Where is it? Yeah, a loops at B, right? I mean, it's an implicit from his language, but let me just be explicit. So what he's saying is that really that there's, you know, a let's say delta such that the alpha star of gamma is equal to the equivalence class built from the delta. And what is delta? Right, I mean, we can write a formula, right? Delta equals what? Yeah, I think it's just alpha, gamma, alpha inverse, right? I mean, that's a kind of silly loop, but it is, I mean, it's not as pictured. I mean, my picture isn't quite the right picture. I mean, that's not the right picture. I mean, delta is, this is delta. I mean, delta is like this. Zoop, zoop, zoop. I mean, that's, is essentially the idea is that you can take, well, but it's more than that, right? Because the claim is that this mapping that is defined up there, right? Take the homotopy class of gamma and map it to this new alpha, gamma, alpha inverse, right? It says is defined and is an isomorphism of these fundamental groups. So let's look at his argument for it and see if we can make sense or head or tail of it, yeah? So what's he proved for us here? He says, since the initial and terminal points of the path match up appropriately, alpha star is well defined. let's let me just go through that right quick. Does that make sense? I mean, if I look at alpha, gamma, alpha inverse, right, of B, where do I go? What's alpha inverse of B? I mean, I really shouldn't be doing what I'm doing anyway. This is not composition of functions, right? So this is an abusive language at a minimum. So let me stop this because it's misleading to you guys. What's that? What did you say? Oh. Let me try a different notation for what we're doing. Okay, so we're looking at alpha, gamma, alpha inverse, right? Think about that join of paths, right? Initial point. Where do we begin? We should begin at B, allegedly. What's that? I'll begin at B. So you're saying I should look at it this way. I should like B, and then by alpha we go to where? C, and then by gamma we go to C, and then by alpha inverse we go to B again. So the point is that this begins at B and ends at B. If we study this path. Well, not just that. What else should we worry about? I mean, to start with, if alpha, I mean, for it to be well defined, we need a bunch of different things. We need the rule, first of all, like the domain to make sense, the codomain to make sense. We need the rule that defines the function actually does go into the alleged codomain. And then after all of that, we need it single valued. I think of all of those things constituting well-defined personally, but I mean, so I think we have all that though, because if we start with, homotopy class here, based where? At C, then at least this, and the thing is, remember we have that the alpha, gamma, can we do this? This is what I'm worried about. Can I do this? Or is that just nonsense? Does that even make sense? But we proved that with fixed endpoints. Does this fit the bill? Yeah? So the fixed endpoints, so I guess we do need the, but, well, yeah. There you go. That's part of the reason we needed to do that last class, was so that this would actually make sense. If we focused all of our attention on loops, we wouldn't actually have what we need to prove this now. Because we need something beyond loops to sort through it, right? Right. Let's see. Okay. All right, so I think Right, and then it goes back to this again. You know, we're combining equivalence classes by joining representatives, and if we use different representatives, we still get the same equivalence class as the point, which is why this function's, well-defined. It's well-defined because I'm using cosets to define it, in short. Not representatives, really. Well, anyway, but maybe this is let's sort through his calculations and see if we can understand why they're important. He says, suppose beta and gamma, both loops at C, right? Which would mean what? That would mean that the equivalence class of beta and the equivalence class of gamma are both elements of the fundamental group of X based at C, right? Among other things. And here's what he does. He's like, okay, then if we look at beta gamma, he's like, that is equal to beta C gamma. Do you guys agree with this? Remember, the constant path doesn't change the path if we multiply it appropriately at the starting or ending point. And since they're loops at C, they start and end at C, so we can put C there and not change a thing. It's using the constant path identity lemma we did last time. And then, ooh, that is sneaky. He goes, hey, I'm going to write that as beta alpha inverse alpha gamma. All right, great. What does that do for us? I have the what? Beta alpha inverse is part of the alpha star. Huh. Multiply alpha on the left of this? What's that give us? Now, why would you want to do that? What are we looking at if we do that? So, multiply by alpha on left and alpha inverse on right. Can we do that, by the way? What is alpha? Alpha goes from B to C. What was gamma? Gamma's a loop at C. Alpha inverse goes from C to B. And so we go, oh, I keep forgetting, I need to read right to left, right? Yeah, I'm sorry, I've been so schooled in function composition going the other way that I've forgotten that when we write joins from left to right, we have to think through them logically as we do, which is that you do this one, then this one, then this one, then this one, right? So if I'm tracing points, it's important that I don't try to trace them this way, because it will be wrong. Thank you. So alpha goes from where? From B to C, and then beta is a loop at C, so it goes to C. Gamma is a loop at C, it goes back to C again, and then alpha inverse goes to C back to B again. So this goes from B to B. This is a loop at B. Again, we go from B to C, C to C, and then C back to B, B back to C, C to C, C back to B. In other words, we go from B to B. So the left-hand side and the right-hand side are both loops based at B. But more importantly, the reason that King told me to do that was that this is what? Alpha star of what? Beta gamma, right? Equals to what's this? Alpha star of beta joined with alpha star of gamma. So Emily and Dr. No, this property that we just proved is the homomorphism property. It says that the alpha star preserves the join of paths, of loops. Right? It takes the loop beta followed by the loop gamma, right, to the image loop of beta followed by the image loop of gamma. It's a homomorphism of loops. It's a loopymorphism. Okay, that's not really a thing, but it'd be fun to call it that. So I said that it's an isomorphism of the fundamental groups. This is just part of it. To prove it's an isomorphism of the fundamental groups, we need to prove that it's also surjective and injective, right? So he says, next, suppose that you had alpha star of beta equal to alpha star of gamma. Our goal is to prove that, in fact, beta and gamma are homotopic, right? They're the same equivalence class of loops. So to do that, I guess I'll just write down the definition, right? And then I believe we can just kind of undo what King did in the last one, right? Which is multiply by alpha inverse on the left and multiply by alpha on the right, which will just give us what? Beta, equivalence class of beta equals the equivalence class of, generated by gamma, which is to say that alpha star is 1-to-1. It's injective. And then finally, how do we prove it's surjective? What would you need to prove it's surjective? So to prove it's surjective, I should let what do you want my notation to be? I'll use a different letter that I haven't used yet. Sigma. Let sigma be an element of pi 1 xb, right? My goal is to, right, I want to find a loop at C that maps to that. So I'll let you guys do the work. Alpha star of fill in the blank equal to sigma. I heard an alpha inverse sigma. I forget. I meant to do that. Sigma alpha. Or more to the, I could just as well write alpha inverse sigma alpha, I think. to draw a picture of what's going on right now, if I can foolishly attempt, oh, why am I putting coordinate axes? What on earth is wrong with me? There are no coordinate axes anywhere to be seen in this. Certainly not. Good grief. So we're looking at a loop at B. Right? We've got this path over here to C, and we're trying to convert the alpha inverse goes alpha inverse so alpha inverse takes C to B, sigma takes B to B because it's the loop at B, and then alpha takes it back to C again. So this is a loop at C, which is what we need to feed to alpha star. So basically, it's a very silly thing. I'm given this loop up here at B. To convert it into a loop based at C, all you're doing is going, I'll just start here and go, whoop, whoop, whoop. I mean, that's it. And it works because this is, of course, alpha inverse sigma alpha inverse, which, of course, is equal to sigma once you cancel the things out using the rules we found last time. So indeed, it's an isomorphism. All right, I think I've spent entirely too much time on this. Are we okay? What is the point of all this? The point of all this is if your space is path connected, then what? Right, if the space is path connected, then the various groups pi 1b for b and x are all isomorphic, and thus the isomorphism type pi 1bx, pi 1xb is well defined, and we just call the fundamental group. So x path connected implies that pi 1xb is isomorphic to pi 1 x b tilde for all b and b tilde in x. So just write pi 1 xb. Seriously, after all of this, pi 1x for fundamental group of x, all right? Now, he says a space X is simply connected if it's path connected and pi 1x is trivial. So that gives us, again, a careful definition of simply connected, which I hurried through at the end of last class, but I'll write it again here. So definition, if X is path connected and the fundamental group is trivial, then X is simply connected. That's a definition. All right. He now says a few words about another way of looking at homotopy in terms of maps from circles. All right, so let's just try to digest this here. He says another way of looking at loops in X based at B, which is convenient for some purposes. All right, he's like, let F from S1. Curses I. First of all, S1 is the unit circle in R2. All right, each map F from S1 to X satisfying what is it? To do F of 1 equals to B determines a loop alpha based at B via the formula. Here it is, alpha of S equals to F of e to the 2 pi is. 0 less than s less than 1. So can I draw a picture? I mean, the idea is kind of this. We've got our, unit interval 1, right? And then here's a point S there. We take that, we wrap it onto this by the exponential. 2 pi I, that gives us a point here. Right, this is my S1, my unit circle in the complex plane, right? And then F gives us a loop over here at B, where B is F of 1. So we're and then he says, conversely, any loop at alpha, rather any loop alpha based at B, arises from F S1 to X satisfying F of 1 equals to B. So what is how do you define F? How do you define F from the loop if you were so inclined? Suppose I'm given the alpha, how do I define the F? F of what? F of e to the I theta equals to what? E to the I theta is a typical point in the circle, yeah? I mean, I could make it easier. I could say a typical point in the circle is e to the 2 pi is, right? If you want to me do it that way, I could do it that way. Then we just put alpha of s here. It's just Moop. Say what again? Integral from 0 to 1. So are you debating whether or not my construction makes sense? Because I guess the question is, are we starting with a loop or a homotopy class? Yeah? I was literally thinking about a loop. You know? Circle, which is a quotient space of the interval 0 to 1. Ah, yes. Mm-hmm. So to pass to the quotient here. So you're suggesting that we look at the quotient map, which constructs this by the pi, which gives us the circle here, and then this is the f, where f is equal to, how's it go? Say again? F composed of pi is equal to alpha. Yes, thank you. That is helpful. That is the interrelation between these ideas, and we should be thinking about that because that is why we're doing this. Yeah. All right. So he says, if the loops alpha naught and alpha 1 base to b are homotopic with endpoints fixed, then the corresponding maps f0 and f1 are homotopic relative to the base points 1 and in S1 and B and X in the sense that there are maps. So he extends the concept of homotopy of paths with fixed endpoints to maps like this. He extends the concept of homotopy from paths with fixed endpoints in the same space, all right, to these functions which are going from S1 to X. So this is an extension of the concept of homotopy yet again. This is a genuine extension. This is not what we've defined already. What's that? Well, equivalent in what sense? Well, what he's saying is that if you have B and you have alpha naught and you have alpha 1, both loops at B, and then you could, okay, that corresponds to F0 and F1, from where? From S1 to X. He says that these two maps are homotopic in a sense. What is that sense? The sense in which those are homotopic he says we have F from S1. So the point is you swap out, and if you read a different book, it will take this as the definition of homotopy. So it's important to talk about this a little bit because sometimes this is used as the definition of homotopy. Rather than unit interval cross unit interval, they'll do circle cross unit interval like this and look at continuous maps from there to there such that f of z0 is f0 of z